average rate of change is the change in output over the change in input. So usually that would be delta y, change in y, over change in x. And we can also write that as f of b minus f of a over b minus a. This is our interval from a to b. So that average rate of change is over an excuse me. Okay, interval. Sometimes if it's x's, it's from x1 to x2. In this notation, it's from a to b. Often your intervals are written in interval notation, x1 to x2, or a to b. Those are the x values, and that's always what goes in the denominator. Sometimes it's called between 2 points. So that if we have points and we're talking x1 and x2, we have a point x1, and then you could call it f of x1, or you could call it x1, y1. And then, of course, x2, f of x2, or x2, y2. Using the f of b and f of a notation, our 2 points would be a, f of a, and b, f of b. So whatever the notation, average rate of change is over an interval. It could be of any length, but it's always between 2 separate points. Now let's look at an example, how we can use this. And we found out that in 1995, there were 91 million tons. Now I'm going to align the data and start at 0. In 2002, we have 102.2 million tons. And that is 2002 minus 1995 is year 7. So when I think about the next bit of data, they said that over the next 3 years, the catch increased 4.8 million tons over the next 3 years. So from 2002, over the next 3 years, there was an increase of 4.8 million tons. So 3 years from here would be 2005. And from 102.2, adding on the 4.8, I now have in that year 107 million tons. And from 1995 to 2005, that would be year 10. The question said, how many, what is the average rate of change over the full 10-year time period? So I can't do separate rates of change. That doesn't make sense. I have to do a single rate of change between 2 points. Average rate of change over an interval between 2 points. So the only 2 points that I'm going to use are starting at 0 and going to year 10, because it wanted the rate of change over the full 10-year time period. So average rate of change, I think of this as on top is the change in catch, because that is my function name, over the change in t, that is my time. I'm working with my t's and not my years, although for this problem it really doesn't matter. So I'm going to put t's in first, 10 minus 0. My catch, 10 was 107 million, minus, to go with the 0, was 91 million. I subtract 16 over 10, and that gives me a decimal of 1.6. So what this tells me is that on average, for 1995 to 2005, the catch per year was about 1.6 million tons of fish. I've got a graph up here. My function f of x is the black curve. The blue line is a line between 2 points. At one point is my x sub 2 value, x sub 1. And for the average rate of change, I'll do the slope, the x2 minus x1. And in the numerator, I'll do the difference in the y values. So this y value is f of x sub 1. And the y value for x sub 2 is f of x sub 2. And you can think of that ratio, the average rate of change, gives me the slope of this line. You're probably also familiar with it as y sub 2 minus y sub 1 over x sub 2 minus x sub 1. So this f of x sub 2 is the same as y sub 2, and f of x sub 1 is the same as y sub 1. And then, of course, we always call those the change in y over the change in x and use the little delta symbols. Now, this type of line is called a secant line. That's just a line between 2 points. And the way the line goes is it crosses between these 2 points. The slope of it is the average rate of change. We could say that it's also the secant line between the x's that are on the interval from x1 to x2. Now, my delta x is x1 minus x2. That's this distance in here. That's delta x. My vertical distance is the delta y. Let's look at a particular function. Let's look at f of x equal to 2x minus 3 plus 5 over x. And I want to look at the secant line between the point where x is equal to 2 and x is equal to 2.5. So that my 2 points, one point when x is 2, I have a y value that will be f of 2. My other point, that is 2.5, my y value f of 2.5. 2 and 2.5 will be my two x's. They'll be in the denominator. Before we set up the fraction, let's go ahead and find our function values separately. Let's look at f of 2.5. 2 times 2.5 minus 3 plus 5 over 2.5. 2 times 2.5 is 5, minus 3, that will give me 2, plus 5 over 2.5 is 2, so this value is 4. F of 2, 2 times 2 is 4, minus 3, plus 5 over 2, that's 2.5. So 4 minus 3 is 1, plus 2.5 gives me 3.5. So let's set up the average rate of change, or you can call it the slope. In the denominator, I have 2.5 minus 2. In the numerator, I have 4 minus 3.5. So that gives me 0.5 over 0.5 gives me a slope of 1. That's the slope between the two lines. I could say this x is equal to 2 and this is equal to 2.5. And I use my formulas and I've gotten the slope of the secant line that's between those 2 points. The numerator would be f of b minus f of a over b minus a to give me the slope or the average rate of change between the 2 points from here to here. Now, when it's between 2 points, we have average rate of change. The difference quotient expands on that a little bit. I'm starting at A and I move a certain distance to get to B. Let's say that distance we'll call H. Now, if A is 2 and B is 4, the distance between them would be 2, so it would be 4 minus 2. So H is the same as B minus A. Or B is the same as A plus H. And I can use this notation to set up a difference quotient in a different form than just A and B. Now it's called a difference quotient because I have a difference on top and a difference on the bottom, and so it's a quotient of differences. And I'm going to take this now and replace B with A plus H. So up here I have f of A plus H minus f of A over B minus A. Now B minus A is H. So this is the difference quotient. This way we can talk about our one number A, and I'm adding certain amounts to it so that I add H and I get up here to B and I have a straight line. I add a smaller H and I get a smaller line between points that are getting closer to A. So let us look at an actual difference quotient in a problem, in an actual function. Okay? Let's let f of x equal negative x squared minus 2x plus 4. And we'll let a equal negative 3. So specifically for this function, I'll have f of negative 3 plus h minus f of negative 3 over h. And what that means is this is my input into the function wherever I have an x. So that this piece inside here goes in exactly the same place as x. So it goes in that x and in that x. And when I do f of negative 3, it's the same thing. It goes in place of x because negative 3 is the input. Let's see what we get here. If I put in negative 3 plus h for x, I have a negative here, and then negative 3 plus h squared minus 2 times negative 3 plus h plus 4 minus, and over here I just have f of negative 3. And then all of that's going to be divided by h. Now I just wrote f of negative 3 there because I find it easier just to go back to the function, find out what f of negative 3 is equal to, and then put it in, instead of putting all the different pieces in as I go. So watch out for the order of operations. For negative 3, this negative stays in front. It doesn't cancel that negative sign. I have, maybe I better write that one down. Negative of negative 3 squared minus 2 times negative 3 plus 4. So watch out for this notation. It's a negative, and then negative 3 squared is 9. Negative 2 times negative 3 is plus 6, and then plus 4. So this is something that students tend to have trouble with, so be very careful. Negative 9 plus 6 is negative 3. Negative 3 plus 4 is 1. Now when I have to simplify this, that's going to take a lot of multiplying out. Negative 3 plus h to be squared is negative 3 plus h times negative 3 plus h. I have a negative in front, and then to do this, I'll have negative 3 squared is 9, and a negative 3h, and a negative 3h is negative 6h plus h squared. I get here and I distribute negative 2, so I have plus 6 minus 2h plus 4. I've got in brackets everything that came from f of negative 3 plus h. Minus, we found out that f of negative 3 was 1. So, everything here now, I'll divide by h, whatever h is, it's h right now. I have to combine terms, I have a negative here, so I still have to go through and simplify a little bit more. Negative 9 plus 6h minus h squared. I distribute the negative sign. Plus 6, well, oh, look over here, I have a plus 4. Let's put those together to be plus 10 minus 2h minus 1. It got shorter over h. Negative 9 plus 10 is 1 minus 1. My constants are gone. And that is supposed to happen. What's left is 6h minus h squared minus 2h. So I'll put the negative h squared. Plus 6 minus 2 is a plus 4h over h. I'll need to either factor an h out of the top. That's what I'll do, and I'm left with negative h plus 4 over h. Or you could think of this as dividing each term by h. So my h's here will cancel because it's all multiplied and divided. And I'm left with negative h plus 4. So my difference quotient for this function is just equal to negative h plus 4. Depending on what h is, that tells me how far away I am from my a, I'll get different values. So this is the way you simplify the difference quotient for this function when a is equal to negative 3.